Hi guys, welcome back. So we're going to continue our use of basic thermodynamic equations to solve pretty easy intro level practice problems here. So this question is asking a reaction of subunit A and subunit B dissociating. Okay, so these are falling apart here. AB dissociates into A plus B at equilibrium. For the reaction written above, the KEQ, remember that's the equilibrium concentrations of products over reactants, at standard state conditions is 214. Okay. Calculate delta G naught for the reaction in kcals per mole. Kcals per mole. Okay. All right. So first thing we want to look at here is try to get a little bit of intuition. Okay. So this thing is falling apart. Does it want to fall apart? Well, that's what we're trying to figure out in free energy terms. But we know already a little bit about the tendency. We know that its KEQ at standard state conditions is 214. Cool. So 214 is equal to A at equilibrium times B at equilibrium all over AB at equilibrium. Does this thing want to go to the right? Does it want to make a lot of products? There's 214 times more A's and B's than there are AB's. Okay? You can see that if you put this over 1. There's 214 AB's for every, or A's and B's for every AB. So yeah, this thing that naturally wants to go to the right. This subunit wants to fall apart, and it wants to fall apart quite a bit. There's very few complexes for the amount of dissociated monomers. Okay, so what should our sign be? Well, we should know that if this thing is going to the right, delta G naught should be negative, right? Negative delta G naughts are spontaneous. So we know something about the spontaneity based on the KEQ. We also should know if this is spontaneous, then also this is spontaneous. Okay? So we're going to use that same equation we had last time. Delta G naught is equal to negative RT ln of KEQ. So spontaneous, this should be spontaneous. Cool. So we know a couple things. We know our KEQ is 214. Great. Natural log of 214. Our temperature, again, is 25 Celsius. And remember what we have to do for that is 25 plus 273.15 equals 298.15 Kelvin. Cool. So there's our 298. Multiply it by that. Now we have to use the right R. So what are we trying to get here? Well, I'm asking you for delta G naught in kcals per mole. So that means we need to use the right version of R to get us kcals per mole. So before we had said that R can be 8.317 joules per mole Kelvin. It could be 8.317 times 10 to the negative third kilojoules per mole Kelvin. Now those are for joules. We're looking here in calories. And remember, there's 4.184 joules per calorie. Okay, so what we have to do here is we take our 8.317, okay, divided by 4.184, and we get 1.987 calories. So that's nice. Our R now is 1.987 calories per mole Kelvin. Okay. That means that our R for kcals, which is 1,000 of those, we divide that by 1,000, means we get 1.987 times 10 to the negative third kcals per mole Kelvin. That's the one we're going to want to use today. Okay, for this one, because we're asked in kcals per mole, we want the one in kcals per mole. The Kelvin, remember, is canceling because it's on the bottom. The Kelvin here, when we multiply it, is going to cancel. So here we'll put that in there. I'm going to erase all this stuff on the bottom, except for that one. Uh, 10 to the negative third. Fix that. So equals 1.987 times 10 to the negative 3 kcal per mole Kelvin. Cool, let's plug that in. One thing you can't forget here is that negative sign. And look what I've done. I've forgotten it. Now, I will tell you right now, that is the most number one common error that students will make when they're first starting to use these equations. So I always make sure that that goes there, okay? So when you're doing these, be sure you don't forget that negative. Oftentimes you'll be working back to the end, from the end to the beginning like I was just doing, and you'll forget that pesky negative sign. So always check that, okay? And again, we'll see how you can use your intuition to check yourself to make sure you don't make a silly mistake like that. But I'm plugging this in, negative 1.987 times 10 to the negative third times 298.15 times the natural log of 214. I get delta G naught, the tendency of the reaction in kilocalories per mole, is negative 3.179 kcals per mole. Alright, so is that the right answer? Of course, that's what we all want when we're taking tests or quizzes or whatever. And in real life, we always want to get the right answer too, not just in quizzes. So we want to make sure that that makes sense. Does that number jive with what we already know about the reaction? Now, we said delta G should be negative, and indeed delta G is negative. Okay, and you notice that when it's 214 to 1, it's just a negative 3 kcals per mole. That is not very much at all. It's a small number, but that means that's a lot of products for every reactant. Okay, so negative 3 is actually quite a large favorable number in terms of the spontaneity of this reaction. Cool? So in this case, the delta G naught for the reaction in kcals per mole is negative 3.179 kcals per mole, and that matches what we predicted at the beginning of this question. Okay, so we're going to take that number and we're going to use that. Again, like I say, oftentimes we'll use this base equation to calculate delta G naught, and we'll use that and flow it into a different equation. So we can use this tendency and then see what really could happen. Or we could try to figure out enthalpically and entropically, is this thing favorable or non-favorable. Alright, so this one is saying the standard entropy change of the forward reaction, and again I'm going to write that up here, remember it's AB falling apart to form A plus B. And do you remember what our delta G naught was? It was favorable. It was, delta G naught was negative 3.179 kcals per mole. So we'll need to use that here in a minute. So the standard entropy change of the forward reaction is negative 30. What is that in symbols here? That is, the entropy change, remember, is delta S. The standard is a little not up at the top. Entropy change, entropy is S and change is delta. So this is the standard entropy change of the forward reaction is 30 cals per mole Kelvin. Let's calculate the standard change in enthalpy. Remember, enthalpy, standard change in enthalpy is delta H naught. So that's what we're solving for. So if we're looking here, which one do we care about? We care about this one. We have delta G naught from the last part of the question. We have delta S naught, negative 30, and we have delta H naught being solved for. So again, I'm going to start out solving the equation without any numbers in it, just for the thing I want to get. Okay, so we know delta G and delta H, so I want delta S, and I want to get delta H on its side. So I'm just going to add T delta S to both sides. That'll cancel it here, and then we'll have delta H on its own. Delta H naught, okay, is delta G naught plus T delta S naught. Okay. Let's review a little bit on spontaneity. Delta G naught here we know is spontaneous, and that's spontaneous when the sign is negative. Delta H does the same thing. And remember, delta S is positive when it's spontaneous. So is this reaction spontaneous? Well, we know delta G is spontaneous. Delta G naught, that's the tendency of the reaction. So altogether, delta H and S must come out also spontaneous. But here we notice delta S, our standard entropy change, is negative. And that means that that is non-spontaneous. And so that must mean that our delta H is spontaneous enough to overcome the non-spontaneous value of delta S. Okay? And we're going to have to prove that delta H is actually a lot more favorable than delta S is unfavorable to give us a net of negative 3.179 kilocalories per mole. So let's plug in some stuff here. We know our delta H. I'm going to plug in negative 3.179. What's our temperature? It's again 25. So I'm just going to do 298.15. and then that's times our delta S. Now let's look at our units here. We had kcals per mole. What is our unit on entropy given? It's calories. Is that going to jive with our kcals? It's not. So we need to divide that by 1,000. So our delta S naught is negative 30 over 1,000 because there's 1,000 calories in a kcal. That is negative 0.03 kcals per mole. So I'm going to put that in here, negative 0.03. And we're going to multiply that by our T. So here I'm going to solve. Negative 3.719 kcals per mole, or 179 rather, plus 298.15 Kelvin times, that's what that's supposed to be, a little time symbol. Here, I'll make it like nicer. Not much better. 298.15 Kelvin times negative 0.03. Units are, again, kcals per mole. Kelvin. And this is also mole Kelvin. So I'm going to add those. 298.15 times negative 0.03 and add that to our 3.179. I get a delta H of negative 12.12 kcals per mole. Okay. That's our delta H. So I took was our delta G from up here, and our T, given in the question, and our delta S that had to be unit converted, right? We had to take our calories and make it kcals. Alternatively, you could have done this into calories by timesing 1,000. It wouldn't have changed anything at all. You would have got the same answer, but in calories. And I didn't ask for anything specifically in a unit, and so you would have been correct either way. Okay. Usually I'll try to specify units, so you have to do it one way, but in this case it wasn't told, so either 12.12 kcals or 12,000 calories would have been correct. 12,120 calories or whatever it is. Okay, does that jive? Well, this is spontaneous, this is also spontaneous, and it's quite spontaneous, right? In fact, if you look at just this piece here, our T delta S is getting subtracted, it's getting lost from our delta H, and just that part, the T delta S, 298.15 times negative 0.03, is unfavorable by 8.94 kcals per mole. Right? That whole T delta S thing is being taken away from delta H to make our delta G. So that whole thing is unfavorable. Right? Delta S wants to be positive, T delta S wants to be positive. In this case, it's negative, so it's unfavorable by 8.9 kcals per mole. And so that means that our delta H has to be a lot larger negative in order to have that subtracted from it and still come out net negative. Cool. So that is a reasonable answer here, because we have a large delta H and a smaller unfavorable T delta S, and so this whole thing comes out net favorable in terms of delta G. Cool. All right. So here's the biggie, the kind of crowning achievement. If you can do all that stuff, great. This is the part where it's a little bit more complex. Okay. So what we have here is calculate the free energy of a solution at 25 Celsius containing 50 micromolar A. Okay. Now a micromolar is 10 to the negative 6 molar A. 100 micromolar B, let's write our equation down just because you don't want to forget it. Okay. 100 micromolar B, so again, micromolar is 10 to the negative 6, it's 1/1,000,000th of a molar. And 200 millimolar AB, 200 millimolar is 10 to the, millimolar is 10 to the negative 3 molar. Okay. So which one do we have more of? Obviously we have a lot more, over 1,000 times more AB than we have either A or B. So in this case we have a lot of products and very few reactants. Okay. So we need to calculate this thing. It looks like we have a lot fewer reactants, but remember what we're talking about here is the product of A and B. So it looks like we have a lot more A and B, but you have to actually solve to figure it out. Okay. So don't just jump to conclusions here and say, oh, there's a lot of AB. This thing is not going to be it may be favorable. We need to check first. Okay, so you might have that intuition. We just want to make sure that it's numerically correct. Okay, so in this case, we're going to try to solve this. Do you remember our delta G naught was negative 3.179 kcals? Okay. Which one are we going to want to use here? Well, we're actually asking for the free energy. And this we probably should call the change in free energy. The free energy change of a solution. So we're going to want to go with this one. Delta G is equal to delta G naught plus RT ln of Q. All right. So we know our delta G naught. It's given to us. We solved it before. We know our temperature, 25 Celsius. The only thing we need is to solve for Q. Okay, and that's where all of this stuff comes in. So do you remember what we said about Q in the last video? Q is our concentration of products. So in this case, it'll be A times B over reactants. In this case, we only have one reactant, AB. And in order to make this thing come out right, we want to convert all of these quantities into molar. Okay. If you remember canceling units before, if we tried to cancel units here, we would only end up canceling one of them, and we'd end up with some leftover stuff. So we want to convert all of these small quantities into full molarity. So to do that, I'm going to add the little multiplier here. It's 50 micromole. It is 50 times 10 to the 6th, or 10 to the negative 6th molar, times B, which is 100. And I'm going to multiply that by 10 to the negative 6 because it's micromolar. And then we're going to do the same thing for AB. AB is 200 millimolar, which is 200, and that's times 10 to the negative 3rd. So what do we get when we solve this? 50 times 10 to the negative 6th times 100 times 10 to the negative 6th divided by 200 times 10 to the negative 3rd. 5 times 10 to the negative 9th on the top, divided by 200, 10 to the negative 3rd. I get Q is equal to 2.5 times 10 to the negative 8th. Do you remember back in the beginning we said that KEQ was 214? I remember that. In this case, Q is much, much, much less than KEQ. So I use a little trick when I'm trying to figure out which way this is going to go, so I can use my intuition. KEQ, write it first, then Q, and then put the bracket in. In this case, Q is much smaller, and so if you were to draw an arrow, the head would go the right way. This thing, because Q is smaller than KEQ, the reaction won't proceed to the right. So this should be spontaneous. Delta G should be what? Delta G should be negative. So that's our prediction. Now let's see if that comes out right. I'm going to erase a little bit of this. Let's start plugging in. Delta G is what we're trying to solve, is equal to delta G naught, negative 3.179, plus R. Which one do we want to use here? What's our unit? Well, this is in kcals per mole. Remember our kcal per mole? It was 1.987 times 10 to the negative 3 kcals per mole, Kelvin, at 298.15 Kelvin, times the natural log of 2.5 times 10 to the negative 8th. Okay, so I'm going to plug that in. I'm going to do just this half first so we can kind of see what's going to happen. This whole thing should be a lot more favorable. It should be negative. So 1.987 times 10 to the negative 3rd times 298.15 Kelvin times the natural log of 2.5 times 10 to the negative 8th. This whole piece is negative 10.37 kcals per mole. And the tendency of the reaction is only negative 3.179 kcals per mole. So real life, RTL and AQ made the tendency of this reaction even more to be favorable. Remember, I told you right at the beginning, we have a lot fewer of A's and B's and a lot of products. We'll have a lot of stuff here and little stuff here. Remember, it's going to try to even things out depending on the reaction. In this case, we know it was favorable to the right, and so it should want to make a lot more. So let's add these together. I'm going to add the negative 3.179, and we get negative 13.54 kcals per mole. Does that make sense? Yeah, we knew Q was less than KEQ. Delta G should be negative, and it should be even more negative because Q is smaller than KEQ. It should be even more favorable. So in this case, this makes a lot of sense. So I hope that helps. I have a bunch more practice problems, and of course the problem set problems you can work with. And hope you enjoyed this one. Bye.